session is concluded by Oliver Brock, a friend of ours, companion of many adventures from Technical University of Berlin. And again, it's about AI, artificial, biological, and embodied.
Intelligence is not just a vague concept, and we shouldn't really let it be a marketing term for machine learning. Intelligence is what we must figure out as roboticists to be able to build the robots that we want to build. But where do we start? Jeff Hinton is convinced that the only way to get artificial intelligence to work is to do the computation in a similar way to the human brain. What if he's right, but also terribly wrong at the same time? The brain, of course, provides strong clues for how to understand intelligence. But I would like to submit to you that looking at the brain at the neural level will not give us the insights that we're really looking for. Why? Well, let me give you an example. If you had to describe the multiplication algorithm implemented on a CPU, would you talk about transistors? No, right? You wouldn't. You would talk about pseudocode, because that's the appropriate level of abstraction for describing multiplication. So I would like to submit to you that neurons are not the right level for understanding intelligence. To understand the alternative approach that I would like to suggest, we have to talk about science and we have to talk about abstraction. Everything that we observe, including intelligence, is the consequence of quantum fields. This is the way that we understand the world today. What you see here is a cartoon of basically all of science, and at the lowest level of abstraction are quantum fields. Derived from that, you see the standard model of particle physics, you see the periodic table of elements, you see objects, and all of these things basically capture some important structure present in the world. Let's call these islands of structure and imagine them in an ocean of chaos indicated by the tangled lines in this graphic. Now, as you rise in the levels of abstraction, something interesting happens. This set of islands seems to branch into two categories. On the left, an inanimate branch, and on the right, an animate branch that I would say contains intelligence. The question offers itself, what's the difference between these two branches, right? How can it even be that there is a difference? Because in the end, everything should be physics. But in the left branch, we found many, many laws that we believe to hold in the entire universe and for all eternity. On the right branch, we, as a scientific community, so far have failed to find such regularities, such law-like structure in the same amount. And the question is, how can that be, right? Where does this come from? I think that the answer to that question is given by levels of abstraction. I think that the complexity in the right branch of how matter interacts with each other is much more complex, and therefore the behavior that we observe in the right branch is much more complex. In the left branch, basically all behavior results from physical fields. Matter interacts via gravitational fields, electromagnetic fields. In contrast, on the right, these interactions between things have gotten more complicated. They're kind of meta interactions. These interactions are built in such a way that they only use physical fields, but they do so in a way that represents state, memory, and even learning. So in the right branch, the interactions between things are active. They actively contribute to the complexity of the observed behavior. Well, basically, this is the idea, right? That these active interconnections differentiate these two branches are a key ingredient to intelligence. On the right branch, there will still be structures of island that we as a community need to go find. They will not represent the behavior of things as they do in the left branch, the laws of physics. They will represent the mechanisms that produce the behavior, because that's actually much simpler to produce. And that also means that these mechanistic principles in the right branch tell us immediately how to build robots. That's why I think robotics is well positioned in order to understand intelligence. I'm part of a research center that's called Science of Intelligence in Berlin. And in this center, we've subscribed to this approach of trying to understand intelligence and robotics. We've identified some of these islands of structure. We call them candidate principles. And I'm going to try to convince you, giving you some examples, that these candidate principles are really fruitful to build robots, to build competent robotic systems, but also to start understanding intelligence. First example, called the lockbox. Biologists study the intelligence of animals using such lockboxes. They're mechanical puzzles that, when solved, reveal some kind of food. Here you see a Goffin's cockatoo, but people also use raccoons, elephants, and mice to basically investigate cognitive capabilities and intelligence in animals. We've built a lockbox for a robot, and we've built a robot to solve that lockbox. The robot needs to analyze the world to figure out where there are good points to interact with the world. Through interaction, it needs to understand the kinematic models of the components of the lock. It needs to infer from its interactions the locking mechanism. It needs to solve that locking mechanism, and once it's done that, it can open the lockbox as you see here. And then this system that we've built is so robust that we can change all kinds of things, including changing the locking mechanism, and this will not phase the system. It will perform reliably and robustly. The way that we built this system is we started with a working system, and then we added these active interconnections that I was telling you about. And through an ablation study, we could show that these active interconnections greatly contribute to the ability of the robot to respond appropriately to variations in the environment, like this new lockbox, like this new lock that was added. So that is confirmation about this principle. I'm going to quickly always show you the people that did the work so you can look at them at the conference. My whole group is here, and you can ask them about the details. Example number 2, in-hand manipulation. You probably think that all in-hand manipulations videos look similar. This one is different, trust me. Let me explain why. Most videos you see actually have a hand that's tailored to the particular task. This is a general hand. Most videos you see use extensive sensing, both in the hand, in the fingertips, external sensing through cameras. What you see here is entirely open loop. There's no data, no learning, no simulation. Yet, this system outperforms on quantitative measures any in-hand manipulation system that I've seen so far. Again, it's the principle of active interconnections that are at work here, but it's actually implemented inside the hand physically. So this shows that these principles that we found in this research center actually apply on different levels of abstraction. The third example that I want to talk to you about is the human visual system. This is a visual illusion. You can actually observe it by fixating on the little black dot in the middle. The rings of dots stops rotating, and when the dots are rotating, the flickering of the dots is reduced. This is what you should see. But this is an illusion, as you may have guessed. The flickering actually doesn't change. Using active interconnections as a basic representational tool, we modeled the performance of the human visual system based on this performance. And this model we could use to predict new properties of the human visual system. I'm going to say that again. We're using a computational model based on active interconnections to predict unknown properties of the human visual system. I think this is a strong evidence that these principles actually allow us to bridge between the artificial intelligent world and the biologically intelligent world. Example number 4. I'm going to call it gradients are everything. By differentiating the active interconnections, we can create a system that generates actions. actually without really specifically designing a system for creating actions, just by looking at these gradients. Here you see a system that's opening a drawer and it's being interrupted by Vito in various ways. The idea is that we can build a system very, very easily. You see here, for example, the system invents, so to say, triangulation. This motion is to estimate depth. It figures out that moving up and down actually improves depth estimation. So this system generates behavior very robustly and does behavior that was never actually explicitly programmed into it. Final example, learning from demonstration. There's a recently published benchmark called Furniture Bench that tests state-of-the-art deep learning-based reinforcement learning and learning from demonstration methods. And based on 1,000 demonstrations, it doesn't exceed a success rate of 40%. What you see here is something based on the principles of intelligence that we've discovered, and it just uses one demonstration to solve the benchmark. So I hope that all of these things together could convince you that there are things, these islands of structure, that really help us build robots and understanding intelligence. So my call to you all and to us all would be, let's go find some islands. Thank you.
Thank you so much, Oliver, also for respecting the time. One question, even two maybe, and then we can enjoy coffee break. Please. Yes. 6th row. Left.
Hello, thank you for the talk. I'll start by saying thank you. One of your earlier papers, your 2015 paper on robotic priors, inspired a lot of my PhD, so I want to say thank you. Now, my question is, you're talking about abstractions, and we had previous talks about abstractions, and Nicholas Roy was asked, where should they come from? And he said, that's still an open problem, and so I want to pose the same question to you. I mean, you showed us these nice results, but I guess where did those abstractions come from, and where do you think they should come from?
Yeah, excellent question. And Nick and I discussed exactly that question this morning in the subway. So where these come from, that's easy to answer. Right now, they're hand-coded. But that's obviously the first step, right? Because we need to be able to extract them. But the answer to that part of your question is also very simple. Because either the system, basically it's a network of recursive estimators. And either the things you measure are within the expectation of your recursive estimators, or they're kind of outliers. If you get outliers often enough, then it suggests that there might be an additional concept that you need to add. I cannot tell you what that concept corresponds to in the real world, but it corresponds to something that you see, you as a robot, see in the world. So I think that this network of recursive estimators that we have will grow automatically based on perception and outliers. And if these additional elements that get added don't end up being useful for improving performance, then they'll just get dropped again. But I'm definitely imagining this system that I showed you being expanded from experience.
A very last one, maybe. Okay. Thank you very much again to the 7 speakers. And this is the end of the session.